Good morning, everyone. Welcome to the Thursday morning session. It's my pleasure to be the chair of the session. To begin today, let me just say the first talk is by Zoom. So if you expect to have a question, maybe you can move to the front so it's easier to get the microphone to you. But this morning, I'm happy first to introduce Taras Banakh from the Ivano-Franko National University of Lviv. Since he's unable to travel here today from Ukraine, he's giving his talk via Zoom. But I would like to, because of the obvious situation, take the opportunity to express my solidarity with the people of Ukraine and their fight for a free and independent country. If only to have had Taras and other colleagues who are unable to travel to be with us here today. Nonetheless, let's welcome Taras, who will speak on automatic continuity of measurable homomorphisms on topological groups. Welcome, Taras.
Okay, thank you. Thank you. So I plan to finish my talk with this slide, but I will start. So today is a big day, by the way. So it is day of Christianization of Kiev Rus. And Kiev Rus was common country for Ukraine, Belarus, and Russia, basically, if you look at the map. So, and it explains partly the reasons of this war. So they're ideological. So Kiev is a common some place of Christianization. Russia would like to have it. It's motherland, let us say. So today also is a day of Ukrainian statehood proclaimed by Zelensky previous year. Okay, and also, so I'm going to the very beginning. Very quickly. And also today is 155th day of this long war. No, nobody expected it to last so long. And because of that, I cannot travel, so it's very pity. So I will talk about classical, also ancient topic called automatic continuity of measurable homomorphisms. And history of this topic traced back to Augustin Cauchy, basically founder of modern calculus. Cauchy compared two properties of functions. One is additivity, preservation of sum, and the other is linearity, so preservation of sum and multiplication, or just multiplication, which in this case is the same. And he discovered in 1820 first that additivity plus continuity implies linearity. So now it is just standard exercise in first year calculus in the university, but nonetheless it is nice here. And Cauchy also asks the question if there are some other solutions to this equation. So he considered this equation as equation on unknown function. So it's called function equation. And there was a question if there are some non-trivial solution, non-linear. And at the time of Cauchy, there was no axiom of choice, no set theory. So he could not answer this question because they even did not know what is function is. What appeared only after creation of set theory by Cantor. And the answer was given by Hamel in 1905. He invented his famous Hamel basis. So he considered real line as a linear space over rationals. And as such a linear space, it has Hamel basis of cardinality continuum. And this Hamel basis can be used to define many discontinuous additive functions. So there are 2 to power continuum such discontinuous additive functions, or more than continuous. And so that is negative answer to Cauchy problem. But there are also positive answers, and they were obtained by famous maybe the best mathematician of all times. So there was 3 papers with basically the same name, title. One paper of Maurice Fréchet, written, I don't know, it is Italian or Latin, Rila Functio Equatio, but it is published in French journal L'Enseignement Mathématique in setting, and 7 years after, in the very first issue of Fundamenta Mathematicae in Warsaw Logical Journal, there were again 2 papers with the same title, Sur l'équation fonctionnelle, of Banakh and Sierpiński, and both of them, in fact 3 of them, prove the same theorem, that Lebesgue measurable additive function is continuous. So at the time, Lebesgue integration theory already has been created. Lebesgue defended his PhD in 1899, just a year before the eve of 20th century. And Banach and Sierpiński write that they just reprove theorem of Fréchet, who used axiom of choice for the proof, and they prove it without axiom of choice. Again, in those times, axiom of choice was very important and discussed. Its validity was not accepted as in our times. So this result is just the first result of huge theory of automatic continuity. So if the function is measurable plus has some algebraic property, additive, then it is continuous. So basically, this problem of Cauchy laid down base to 2 sciences. One science is called functional equations, and it is developed, for example, by the group in Katowice, very active. And the other science is automatic continuity of homomorphism. They are interrelated, of course. Okay, and what is the reason? So why Lebesgue measurable additive functions are continuous? Okay, and the answer is explained by another very important and seminal paper published in the same first volume of Fundamenta Mathematicae by Steinhaus this time. So Steinhaus published the paper Sur la distance de points dans les exemples de mesures positives and prove this theorem, that if we have a measurable subset of positive Lebesgue measures, so large in the sense of measure, then all distances between points, so all such differences, they form a neighborhood of 0. And this theorem implies very easily this automatic continuity, theorems of Banach and Steinhaus. Yes, theorem of Steinhaus was motivated by result of Sierpiński. This theorem of Steinhaus was very soon, so just 16 years, because 40 it is the year of appearing of the book of Weil, L'intégration dans le groupe topologique, and the result was proved more or less 4 years ago, before. And Weil proved that analog of Steinhaus for locally compact topological groups. So for if we have a set of large positive Haar measure in each locally compact group, there is Haar measure. I will explain in the next slide. So when there is a set of positive Haar measure, then this difference, but written in multiplicative terms, is neighborhood of identity of the group. So both theorems are very important. Okay. It writes me that we have only 10 minutes left on this Zoom. I don't know what does it mean. Okay, and as definition of Haar measure. Haar measure in topological group, it is any non-zero, so non-trivial, left invariant sigma additive measure on the sigma algebra of Borel sets, such that each compact set has finite measure, and any Borel set can be approximated from within by compact sets. So for any Borel set, any real number smaller than the measure, we can find compact set in this Borel set, which has measure larger this as close to this lambda as possible, and lambda can be infinite, basically. Okay, and Haar in 1933, by the way, that is the year of his death. He is Hungarian mathematician, and he was not killed, as one can suggest in these times, but he died of cancer. And he proved that every locally compact group has a Haar measure, has such a measure, and this measure is unique up to multiplicative constant. Weil, just 3 years after Haar, proved that Haar measure can exist only on locally compact groups. So if the group is not locally compact, no Haar measure. If locally compact, there is such a measure. Okay, and now we discuss another very important property of topological groups, which is not so known, by the way, but as it deserves. So this notion was introduced by Arkhangelsky, who suggested this notion as a topic of PhD dissertation of Guran. Guran is our dean at the moment. But Arkhangelsky called this notion omega boundedness at those time in 80s. And Tkachenko and Arkhangelsky, when have written the famous book in topological groups, they renamed this property to omega narrowness. And because of that, I wrote these 3 authors as inventors of these important notions. So Arkhangelsky, Guran, and Tkachenko invented or suggested this definition. Topological group is omega narrow if it can be covered by countably many shifts of any non-empty open set. So it is kind of Lindelöfness, but such related to group structure. For any non-empty open set, we can find countably many translates, and those translates cover the group. The class of omega narrow groups was investigated by Guran, and it was his PhD dissertation, and he proved this characterization. Omega narrowness, it is the same as being a subgroup of Tikhonov product of second countable topological groups. And he also proved that this class of omega narrow groups has many nice inheritance properties. So this class is closed under products, taking subgroups, continuous images, and contains all topological groups which are separable in the law of countably cellular, and many other countability properties. They imply this omega narrowness. So the omega narrowness is very weak countability property, but it's very helpful. And this is a paper of Guran from those times and his picture. Okay. This notion was used already. A function from a locally compact group to any topological space is called Haar measurable if pre-images of open sets are measurable with respect to the Haar measure, which is unique up to multiplicative constant. Measurable means that they can be approximated by Borel sets from inside and outside, and actually by compact set from inside. Okay, and there is such a nice theorem. I don't know who proved it. Probably maybe Weil, but it involves this new notion of omega narrowness, which did not exist those time. So anyway, there is such theorem which says that any Haar measurable homomorphism from locally compact topological group to any omega narrow topological group is continuous. So it is one of automatic continuity results. Measurability plus algebraic structure plus smallness of the range. Range must be omega narrow, then this homomorphism is continuous. Okay, and the proof is very simple. Just one slide. So we have this Haar measurable homomorphism. Okay, would like to prove continuity. So take neighborhood of identity in the range. replace this neighborhood by smaller neighborhood V, which is inscribed in this larger with the square. Okay, then use omega narrowness of the image, because omega narrowness is inherited by subgroups, and cover this image of X by countably many translates of V. I will write something. So maybe we will have problem in 4 minutes because it will disconnect us probably. So cover H of X by countably many translates, okay, of this Y. Take pre-image. This pre-image is hard measurable because the homomorphism is hard measurable. And since this pre-image cover X by countably many translates, okay, it has positive hard measure. And then we use Steinhaus way that this set is neighborhood of the unity, and this A minus 1 sits inside of the pre-image of this large neighborhood because V was chosen this way. And this gives you continuity in the identity. And this continuity implies continuity everywhere because it is homomorphism. So such a very simple, but nonetheless very nice and important theorem. This theorem suggests the problem with this narrowness. Could we remove the narrowness from this result? So if you analyze the proof, we see that the narrowness is used very essentially. Okay, so we cover it Y by countably many translates of the interval. So this, if it is true, it is not trivial. Okay, and the story here develops this way that yes, it is true if the image, the range is locally compact. So that is theorem of Kleppner, who used some representation theory of locally compact groups, or not trivial. And he proved that higher measurable homomorphism between two locally compact groups is continuous. So the paper of Kleppner from 98, there was a small gap in this paper, and he fixed this gap 2 years later. Okay, and so what without local compactness? 10 years ago, Kuznetsova, she is probably Russian, but she is working in France now. And he proved that under Martin axiom, every hard measurable homomorphism from locally compact group to everywhere, any topological group is continuous. So we have, if Martin axiom can be removed from this theorem, and my first main result, today I have program minimum and maximum. Program minimum is just a noun for main results, and maximum to explain why they work. So in program minimum, my first result that it is indeed true. Every hard measurable homomorphism from a locally compact topological group to any topological group is continuous, and it does not require omega narrowness. Okay, so any hard measurable homomorphism from locally compact topological group to arbitrary topological group is continuous, and this in this context is the final result. And what we can do next? So what happens for measurable homomorphism on arbitrary, not necessarily locally compact topological groups? So in this case, by veil result, no hard measure exists, so we can not speak about hard measurability. Okay, but we can speak about universal measurability, measurability with respect to any measure. If hard measurable, we can take any possible measures which are not any radon. So what is radon measure? It is just HR measure without left invariance. So radon measure is non-zero sigma additive Borel function Borel measure such that any compact set has finite measure and any Borel set can be approximated by compact set from within. Measure of Borel set can be approximated by measures of compact subset of this Borel set. And subset is universally measurable if it is measurable with respect to any radon measure lambda on X. And measurability means, again, we can put this A into Borel set, which is larger, and find smaller Borel set such the difference has zero, measure zero. A function between two topological spaces is universally measurable if the preimage of any open set is universally measurable. Okay. And now we can ask such a naive question. Is it true that universal measurability implies, because we have seen that higher measurability implies continuity and universality is stronger? Is it true? And the answer, of course, not true, because so two free groups of rank 2 and obvious isomorphism between those two groups is discontinuous, but it is universally measurable because those groups are countable, so everything is measurable there. So such a question is not good about, but we have a question due to Christensen. Is it true that each universally measurable homomorphism between Polish group continues? And this question turned out to be very difficult. Okay, at first, Christensen himself answered this question positively, affirmatively for groups whose range is balanced. So topological group is balanced, or else it is called also sin group. Balance if it has a base of neighborhoods consisting of this base of balanced neighborhood. Balance means commutative with all elements. X times u equal u times x, or x u x minus 1 is u, is the same. Okay, and commutative groups are of course balanced. And Christensen in 1970 first proved that each universally measurable homomorphism from the Polish group to a balanced omega narrow topological group is continuous. This again, I exaggerate, of course, because omega narrow did not exist those times, but it is just one line generalization of what he proved. Okay, and preparing this talk, I discovered that Christensen died this month, very pity, the 1st of July. So this talk can be also dedicated to the memory of Christensen. And how Christensen proved his theorem? He proved an analog of Steinhaus-Weil for the notion which he invented. It is also very, very important in topological algebra and Banach space theory. And it is called Har-null. A subset, universally measurable subset of topological group is left Har-null if for usual Har-null, it means that for fixed Har measure, the set has measure 0. Here, for each set, prove theorem which is analog of Steinhaus-Weil. If a universally measurable subset of a Polish group is not left Har-null, so it is large in this sense, then there is finitely many points such that this A minus A, but finitely many conjugated. Finitely many conjugated identity. And if this A is balanced, so if it commutes with this X, then A times A minus 1 just analog of Steinhaus-Weil, and this analog in the same way as that folklore theorem I explained, it implies this automatic result. Any universally measurable homomorphism from Polish topological group to balanced omega narrow topological groups is continuous. Why? Because we have neighborhood of identity in Y, inscribe balanced neighborhood V, take countably many translate pre-image of this V. This pre-image balanced is balanced subset of X. This A minus I is neighborhood of identity, and that's it. Okay. Yes, and now the question about this balanced. This word from the Christensen theorem, and which was just very recently resolved by Christian Rosenthal. I hope that he is in this lecture room. If he is there, please raise your hand. I don't see. Okay. Aha. Okay. Nice to see you, Christian. So he proved this nice theorem in 2011. So this is COVID year. That universally measurable homomorphism from Polish topological group to any omega narrow topological group is continued. Again, this omega narrowness I just added. Its notion existed, but I don't know why Christian did not use it. Yes. And the question now, what about this omega narrowness? Could we delete it from theorem same way as we deleted it from theorem of this folklore for higher measurability? And the answer is yes, we can delete this omega narrowness, and moreover, we can delete even Polishness from here and replace it by Czech completeness, which is much more general notion. Okay, so what is Czech complete? Topological group is Czech complete if it is homeomorphic to a G delta subset of some compact Hausdorff space. In particular, all compact spaces are Czech complete, and all locally compact groups are Czech complete. And measureable spaces are Czech complete if and only if their topology is generated by complete matrix. So this completeness, not topological. Polish groups are Czech complete, and this is the second my main result, which I would like to announce at this conference, is this one. Any universally measurable homomorphism from a Czech complete topological group to any topological group is continuous. Okay, so that is generalization of Rosenthal and Christensen. And now let us turn to other kind of measurability, which is bare category measurability. There is measurability in sense of measure and measurability in sense of bare category. And the main notion here is bare property. A subset of topological space has bare property if it belongs to the sigma algebra generated by open and meager sets, so extension of Borel by meager. And bare property, it is the same as being open modulo meager. So is almost open, plus minus meager sets. For bare categories, there is also analog of Steinhaus-Weil, which was proved by Picard, Sophie, not Emile, and Pettis in 1951. This Sophie, Picard is very interesting person, by the way. She says that she is woman, mathematician, which is not very often even now. In those times, it was very rare. She was born in St. Petersburg. Picard is the name of her father, not husband. Father was Swiss, and she was educated in Smolensk, and then in 25th year, she emigrated back to Switzerland. And there, with some difficulties, she became professor of mathematics in this Neuchâtel Neuchâtel University in Switzerland. She published it, I don't know, maybe that is her dissertation because it's very large, 200 pages. And the title of this dissertation resembles the title of Steinhaus paper, you see. Sur les exemples des distances de l'ensemble de points d'espèce euclidienne. That is, Picard proved this theorem for Euclidean spaces. Okay, and Pettis generalized to any topological group. And they proved that if we have a large non-meager set with a bare property in any topological group, then the set of distances, or this A minus A times A minus 1 is neighborhood identity. Okay, in this case, by the way, the group must be bare, also non-meager, because it contains non-meager set. So that is Steinhaus-Weil, but for bare category. And in the same way, now measurability. A function between topological spaces is BP measurable if preimage of each open set has the bare property. I should make this. Yes, has the bare property. This is bare category analog of measurability. And in the same way as Steinhaus and Weil implied automatic continuity result for hard measurable homomorphisms, the same way Picard and Pettis imply this theorem. Every BP measurable homomorphism from non-meager topological group to omega narrow, again, topological group is continuous. And the argument is exactly the same. Take neighborhood in the range, inscribe smaller neighborhood with the square, cover by counting the many translate of this smaller neighborhood, take pre-image, apply Picard Pettis, and obtain continuity. Okay, the same problem. What about possibility to remove omega narrowness from this theorem? And this time, not so optimistically, partly, we can not remove, but only move. So we can move this omega narrowness from the range to the domain. And this is our sad result. Any BP measurable homomorphism from omega narrow Czech complete topological group X to orbit, okay? So Y was moved from, omega narrowness was moved from Y to X, but plus Czech completeness. Okay, and again we have partial answer. We can partially move, but for universally BP measurable homomorphism. Okay, what is universally BP? A subset of topological space has universal bare property if for any closed subspace of X, the intersection has the bare property in subspace. For example, Borel sets, they have universal bare property, or analytic sets, they have universal bare property. And function between topological spaces is universally BP measurable if the preimage of any open set has universal bare property. And this previous theorem with omega narrowness implies this one without. Any universally BP measurable homomorphism from Czech complete topological group to arbitrary topological group is continuous. And the argument here is simple, basically, because each Czech complete space is K-space. So continuity, it is the same as continuity of restrictions to compact sets. Okay, so take any compact set, and we would like to prove that restriction is continuous, sufficient because of Czech completeness. So take this compact set, generate a subgroup. By this compact set, this subgroup will be sigma compact, take closure, and it will be omega narrow. Okay, and now universal BP measurability implies that the restriction is BP measurable, so continuous. So this restriction is continuous and H is also continuous. It's very simple corollary of the previous result, but it does not use omega narrowness, at least apparently. And a summary of those results discussed so far. For a homomorphism from Czech complete topological group X to arbitrary topological group Y, the following conditions are equivalent. H is continuous, A is Borel, preimages of Borel, of open sets are Borel, or Borel's preimages of Borel are Borel is the same. H is universally measurable in the sense of measure, or H is universally BP measurable in the sense of Ver category. And this is open problem. To my taste, it is very good problem. So I invite you to struggle. I don't know how to prove it. And we have partial answer that if X or Y is omega narrow, then yes. BP measurability implies continuity. Without omega narrowness, who knows? But probably yes. Okay, now I still have some time. Yes, at least 10 minutes if you did not add me anything more. So I can explain the reasons. So how we remove this omega narrowness of Y. So we have these two theorems. Continuity of Haar measurable homomorphism and continuity of BP measurable homomorphism. And those two theorems are in fact corollaries of one theorem. One theorem, I stated it here. It involves many notions which should be explained. So let X be a non-meager K analytic topological group. And I is CCC left and sigma ideal with functionally Borel base on X. Such that any Borel subset of X is, this is functionally Borel modulo ideal. Then continuity of any homomorphism, it is the same as measurability with respect to this extension of sigma algebra of Borel set by the ideal. And those two theorems above, they are just partial cases for ideal of sets of measure 0 and ideal of meagers. Okay, so now let us explain some concepts which appear in this second theorem. Okay, the first notion, which is very, very good, is K analytic. This is non-standard definition of K analyticity, but it is very short and very helpful. Standard, it is via multi-valued maps, and because of that, these K analytic are not so known as they deserve to be. So topological group of space is K analytic if X is continuous image of Lindelöf-Chev complete space. So it is direct generalization of analyticity. Analytic if it is continuous image of Polish. K analytic, continuous image of Lindelöf-Chev complete. And K analytic, non-meager K analytic topological groups, they have very nice characterization. Okay, so topological group is non-meager and K analytic if and only if it is omega narrow and Czech complete, if and only if it is Lindelöf and Czech complete, if and only if it is countably cellular and Czech complete. So those are countability properties implying omega narrowness. So they're equivalent to omega narrowness, and it is the same as to have some normal compact subgroup or balanced compact subgroup such that quotient group is Polish. So it is something like Polish times extension of Polish group by compact group. It is the same, all those properties are the same, and so we use this characterization working in omega narrow Czech complete group. They are very nice. They have those properties. Okay. Now what is functionally Borel set? Subset of topological space is functionally Borel if it is a preimage of Borel set in a Polish space. We can take countable product of real lines for this Polish space always. Okay, and this also such strange notion as functionally arbitrary. Subset is functionally arbitrary when it is preimage of some subset of Polish space. Okay, some strange notion. Okay, and Bo X, it is sigma algebra of Borel set, and Ba X, sigma algebra functionally Borel set. They are called also Bear set, but I would prefer to use functionally Borel because Bear, it is overcharged with many different notions. Bear space, Bear property, what is this Bear subset is functionally Borel. Okay, now about ideals. A family of subset is sigma ideal. Everybody knows what is that. Maybe I will not spend time. Sigma ideal has functionally Borel base if any set of the ideal can be enlarged to functionally Borel subset in the ideal. CCC, countable H condition, means that any disjoint family of Borel I positive sets is countable, and this by X plus minus Y is just sigma algebra generated by Borel plus sets in extension of the sigma algebra of functional Borel subset with this ideal. And example, ideal of meager sets of countably cellular Tikhonov space is CCC and has functional Borel base. Can be proved. And sigma ideal of Haar measure of sets of Haar measure 0 in omega narrow locally compact topological group is again CCC has functional Borel base. This first ideal has functionally F sigma base, and the second functionally G delta base. Okay. Ideal on topological group is left invariant is clear. Was that subset positive is clear, and we have such a ideal version of Steinhaus-Weil-Picard-Pettis simultaneous. I consider this also folklore result, probably. So it says that when we have left invariant CCC, sigma ideal with functionally Borel base on omega narrow Czech complete topological group, then for any I positive set in this extension of the algebra of functionally Borel sets with sets in ideal, this set is the neighborhood of then this set is neighborhood of identity. So it is weaker than Steinhaus-Weil and Picard-Pettis, but sufficient for automatic continuity results. Okay, and the proof is again very simple. Since this ideal has functional Borel base, we have this I positive set in this sigma algebra. Then this I positive set inside contains a I positive functionally Borel set, because you can what is set in the sigma algebra? It is functional Borel plus minus set in the ideal, and ideal has functional Borel base, so you can just remove what is not necessary. Inside you have functional Borel set. And this set B, it is subset of our topological group, which is omega narrow Czech complete, so K analytic. Functional Borel subset of K analytic remain K analytic. So this is B is K analytic. We have CCC, which says that there is only countably many pairwise disjoint shifts. Take maximal set. And this maximality implies that X is equal to M B B minus 1, okay, because you cannot insert any other shift, so it intersects. And our group is non-meager, M is countable, so B minus 1 is non-meager, and apply Picard-Pettis to this K analytic, because K analytic spaces have their property, and you get it, okay. And this ideal version implies this corollary. If we have left invariant CCC sigma ideal with functional Borel based on omega narrow Czech complete topological group, then any measurable homomorphism with respect to sigma algebra extension of Borel's by this ideal, again to omega narrow topological group is continuous. So the proof again is the same using this kind of Steinhaus-Weil Picard patties. Okay, and now the trick is to remove omega narrowness from Y. How to remove this omega narrowness? Because it's everywhere. In all this argument, you need this omega narrowness. How to remove? This will be done with help of notion of semi-measurability and suitable theorem about non-measurable unions. And I have a question: how much time do I have? Do you add me some time, which was?
Because we had a bit of a technical difficulty, so if you could, maybe another 5 minutes is enough.
I hope so. Yes, thank you.
Okay, maybe 5 minutes. Yes.
Okay, thank you. This also is important notion of semi-measurability. It is half of measurability, by the way. What is that? Let I is a sigma ideal in topological space. Subset of this X is called, with such strange symbol, AI semi-measurable if for any K analytic subset A, if the intersection of this K analytic set with other set, which should be semi-measurable, if this intersection is large in the sense of I, then inside of this intersection you can find K analytic large set, I positive K analytic. Okay, and it turns out that if we have nice ideal, left invariant CCC, we don't need left invariant here because it is about topological space. It's just CCC sigma ideal is functional Borel based on K analytic space, such that we have these Borel sets, they are almost functionally Borel. Then subset is measurable with respect to this sigma extension of sigma algebra Borel set by ideal, if and only if the set and complement are semi-measurable. Okay, so semi-measurability is just two halves of measurability. Okay, and now this is crucial result, which is called four-pole theorem. There are 4 poles: Brzuchowski, Tikhon, Jegorek, Relin-Narzelski. Theorem from 79. And it says that for any sigma ideal with Borel based on Polish space, any point finite family of small sets with large union contains a subfamily whose union is non-measurable. Okay, and this corollary implies another automatic continuity result. If we have left invariant sigma ideal with Borel based on Polish group, for any measurable homomorphisms to arbitrary topological group Y, there is no omega narrowness here, you see. Then for any neighborhood of the unit in Y, the pre-image should be large. Okay, and if it is large and I has CCC, then we have this Schenhaus, Weil, Picard, etc. property, and CCC implies that H is continuous because this H minus I minus U 4 times multiplied will give you a neighborhood. Okay, and how to prove it? Just apply this Brzuchowski, Tikhon, and Grzegorek. If the pre-image is small, okay, then you can cover by this small set all X and then apply Brzuchowski, Tikhon, and Grzegorek and find some subset which should be pre-image of open set, but on the other hand, it is non-measurable and it will be a contradiction. Okay, and this is essential result which allows you to move from Polish to Czech complete. This generalization of 4-pole theorem obtained by Banakh, Ralowski, Zhebersky in previous year, let's say. So it says that the same as 4-pole theorem, only the conclusion is semi-measurability. This 4 poles says that the union is not measurable, so it is one of those halves is not semi-measurable. This theorem says that exactly that union is not semi-measurable. Then we have the same semi-measurability for functions. Function is semi-measurable if the image of open set is semi-measurable, and this theorem implies again automatic continuity theorem. For any left invariant sigma ideal with functional arbitrary base, here this very strange notion appears. On omega narrow Czech complete topological group, any semi-measurable homomorphism to any topological group without any omega narrowness here, and pre-image of any neighborhood is large. And if ideal has CCC, then we apply this Steinhaus-Weil-Picard multiplication of 4 copies and obtain neighborhood, and it will be continuous then. Okay.
Taras, I'm worried you're going to be cut off soon. We're going to lose time soon. So if you could please maybe wrap up in the next minute, that would be good.
Yeah, it is last slide. So we obtain these 2 theorems, and this is my preprint where everything is written. And thank you for attention. Comment questions. You see here this baptization. And Slava Ukraini, Героям Slava. It's now main slogan. So thank you. Yes. So this is the end.
Are there any questions? Christian Rosendahl.
Yeah, Taras, this is Christian Rosendahl. So you have this this statement about a difference of 4 sets. I don't know. Are you there? Okay.
So
yeah, sorry.
yes, I'm here. So there is a statement about difference of 4 sets. And what next?
Yes, so you have this statement about differences of 4 sets. I mean, usually in the Steinhaus theorem and Bay theorem, you get difference of 2 sets. Do you get consequences about H-null, about the sets that are not H-null in Polish groups from this? Because that was sort of the initial approach to Christensen's theorem. This problem. So
no, I understand. The problem is that H-null in non-locally compact groups, they have not CCC.
yeah.
So this cannot be applied, at least. So at the moment, I can answer only this.
Yeah.
So because of lack of CCC, this is not applicable, but it does not exclude that something like this exists.
Okay, thanks.
Are there any more questions? No, I don't think there are. I just would make one linguistic comment. I think the paper on page 2 of your slides by Frichet was in Esperanto, if I'm not mistaken, but I'm not positive about that. Anyway, so, but if there are no other questions, maybe we can thank Taras one more time. Thank you. Thank you, Taras. So bye-bye.
Best greeting from Lviv. Have a nice conference. Yeah. See you the next TOPOSYM probably. Or in Lviv.